Hey everybody, it's Dr. J, and today we're talking about the periodic table and properties. Let's talk chemistry. So a couple of different things I just want to point out, right? The properties of the elements follow a periodic pattern, right? So we understand that pattern. It's the periodic law that Mendeleev came up with, right? And this is now we know, right, that they're determined by valence electrons. Now, because of this, right, this makes sense to our properties as we talked about. The same column, you're going to have the same properties. The same period, we're going to see a pattern that repeats itself. Okay. Now, one important thing you guys want to understand is that we have noble gases. Okay, so noble gases, eight valence electrons, and because there's eight valence electrons, they're going to be non-reactive. Okay, so these are the group over here that's 8A. All right, those is neon and all those type of gases. All right, so they're noble gases. They're very non-reactive. They're inert, and the electron configuration of those noble gases are very stable. All right, so basically, you're very stable if you're a noble gas. Now, elements with electron configurations that are close, right, to noble gases, they're going to be very reactive, however, right? Because they're trying to attain this noble gas electron configuration. So basically, everybody in your head, think about this, right? Everybody's trying to get it, all right? So in this case, everybody's trying to be like a noble gas. The reason being is that the noble gases are very, very stable, right? And in this case, these elements are trying to become very, very stable, okay? So if we think about everything we learned, right, with valence electrons, we understand now that alkali metals have that plus one charge, right, plus one oxidation state. And we understand that you got a plus one charge. That essentially means, right, we need to lose an electron to become like our good old friends, noble gases, right? Because if we lose that electron, right, now we're stable. Because we understand, right, this whole X block, right? We got in this case lithium 1s2, 2s1, right? Sodium 2s2, 3s2, etc. Right, going down. Okay, we understand, right? With the s's, they got that one electron in that s orbital. That one electron, in order to become stable, is going to be lost, right? To get back to my completely filled orbitals. That's all we're trying to do here, right? Because valence electrons, in this case with noble gases, are completely filled orbitals. And everybody wants to have a completely filled orbital in order to be stable. Okay, and even if we look at halogens, right, we're going to look at one last main group. Halogens, we understand in this case they got that negative one charge. In this case, halogens need to gain that one electron in order to become stable. So that's why we got this negative one charge, right? Because they need that extra electron in order to get me stable, right? To get and become stable. Okay. And this is what we see here. Everybody wants to be a noble gas. That's it. Everybody trying to get it. Everybody wants to be a noble gas. So when it comes to the electron configurations of ions, right, it makes sense now when we were talking about everybody trying to be like a noble gas. Right? So for example, if we're talking about cations, cations are forming when the atoms are losing their electrons from the valence shell. So if we look at our aluminum atom, we understand that aluminum is going to have, in this case, three of those valence electrons on the outermost shell. So we do our electron configuration. It's 1s2, 2s2, 2p6, 3s2, 3p1, right? This is aluminum's normal electron configuration. However, when we think about the ions, right? If you think about all the ions, those ions are losing electrons in the valence shell. So when we talked about aluminum in the past, right, when we had to know that, okay, it has a plus three, well, how do we know? Why do we know, right? Why was it plus three? We're about to talk about the why, right? 1s2, 2s2, 2p6. If we look at the aluminum plus three ion, this is the electron configuration. This is telling me that I have lost three electrons. Where did those 3 electrons, right? Where did they go? How were they lost? They're lost from the outermost shell. 3s2, 3p1, right? So those aluminum atoms lose these electrons here to become an ion. In this case, a cation. And we can see, right, what that looks like. Because now, right, when we do the electron configuration for this aluminum ion, right, we're going to get the 1s2, 2s2, 2p6. So we can see it over here, 2s, 2p6. What do we notice? Right? Our orbitals are completely filled. They're stable, right? So in reality, when these things are becoming, right, from a neutral atom to an ion, they're actually becoming stable because they're losing those extra valence electrons, right? And now they got this noble gas electron configuration here. Same thing is for anions, right? In this case, we understand that anions are formed when nonmetal atoms gain electrons. Now let's take that a step further. Now we understand that anions are formed when nonmetal atoms gain enough electrons to have 8 valence electrons, right? Because once again, we're all trying to be like who? Noble gases, right? We're trying to get this noble gas electron configuration. So when we think about sulfur, sulfur has 6 valence electrons, right? We do our sulfur atom electron configuration, 1s2, 2s2, 2p6, 3s2, 3p4. But when it's an anion, right, in this case, it's going to be what? It needs to gain 2 electrons to become this anion. Now, why in this case would it want to gain electrons? Because it's easier to gain those electrons, right, than lose 6. So it's going to gain 2 more electrons in order to get to the noble gas electron configuration. In this case, the closest one is right here, right? Neon over here. But when we draw this out, do the diagram, 3s2, 3p6, 8 valence electrons. It's stable, right? This is with everything, every single cation, every single anion, right? Now we understand, right, the why behind, why they're losing, why they're gaining these different electrons. Okay. And then when we talk about transition metals forming cations, right, the first electrons are going to be removed, right, are valence electrons, right, in all the cases we mentioned before. So let's look at an example, right? Iron. This is the electron configuration here, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, right? So in this case for iron, we talked about how transition metals can have multiple oxidation states. 2 of those are going to be +2 and +3. So when we look at this cation, we can see, right, that if it's +2, that means iron, what happened here? Iron, right, if we look over here, it's going to lose 2 electrons. Now, where did those 2 electrons come from? This is very key to understand, right? Those 2 electrons were lost from the 4s2 orbital, okay? So when we actually do our iron cation electron configuration, it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So we didn't take those electrons from our 3d orbitals, we took it from the 4s orbital, right? And we understand, right, because 4s, it has lower energy than my 3d orbital. So it's a lot easier to take away some electrons in a lower energy orbital. And then when we go to +3, right, in this case, we're going to take the electrons from the 4s2, but now, right, we can go to the next one up, 3d. Okay. So then we're able to take it from our 3d orbital now. Okay. So that's how we're looking at transition metals, right? In this case, the lowest energy orbital is what's going to be taken. Then we can move on into the d orbitals, okay, in this instance. So when we go to do our orbital diagram, it's looking like this, right? 3d5, we don't have any electrons in the 4s, right? We have all our electrons in our d orbital. And once again, this is just because, right, we got to understand this transition metals. But paramagnetic and diamagnetic. Paramagnetic is basically your electron configurations, right, are going to give you unpaired electrons. Okay. So if you got an unpaired electron, then you're going to experience, right, a net magnetic field. Okay, so basically you're going to be attracted to your magnetic field if you have unpaired electrons. All right, so paramagnetic elements, they do exist. They're actually rare. The most common one are actually diamagnetic elements. So when we talk about diamagnetic, we're talking about electron configurations that are resulting in paired electrons, right? And we understand now why we're going to see more paired electrons is because everybody's trying to be stable, right? So you need, in order to be stable, sometimes you got to be in pairs, right, to completely fill our orbitals. So with diamagnetic, right, that means that it's going to be all paired electrons in our atom or ion orbitals, okay? And because they're paired, then we're not going to experience a magnetic field. Okay, so it's actually going to be repelled by our magnetic field. We're actually going to go over this once again in the upcoming videos, but we're just mentioning it now. Okay, so that you guys, once you are exposed, you are ready to go.